The central premise of this channel is that aging and disease are biochemical processes that happen over many decades. And if we can track well-established biomarkers of organ and systemic health, can aging and disease risk be slowed? So with that in mind, let's take a look at blood test data from Jiraiman Kimura. Jiraiman was a supercentenarian. This is defined as anyone living to older than 110 years old. In Jiraiman's case, he lived to 116, and his data were recently published in this study here, Clinical Course of the Longest Lived Man in the World, a case report. All right, so there are three main time points that were reported in that study. When Jiraiman was 111 and a half years old, 113.3 years old, and 115.7 years old. And then I'm gonna cover about half of his blood biomarker data. I may go into part 2 in a separate video. So what's good in terms of his blood test results? What's bad in terms of his blood test results? And if you notice, creatinine hasn't been boxed. We'll see in a few slides that creatinine data is incomplete. So first, what's good? So Jiraiman's fasting blood sugar, so his fasting glucose levels, as shown here, were 80, 111, and 87 milligrams per deciliter. So let's put that data into context. So here we're looking at fasting blood glucose levels as a function of age, all the way up until 88 years. And I'm only going to cover data for men as this relates directly to Jiraiman. So as you can clearly see, glucose increases during aging. And if we take Jiraiman's average data over these three measurements over this 4-year period, his average is 92.7 milligrams per deciliter, which puts his data closer to someone who's in their 30s rather than someone who was in their 110s. So what about all-cause mortality risk? So there's a J-shaped curve for all-cause mortality risk, with values less than 80 being associated with an increased all-cause mortality risk, but then also, when considering that glucose increases during aging, relatively higher levels, so higher than 94, are also associated with an increased all-cause mortality risk. And we can see by putting Jiraiman's average data that he's close to the lowest portion of the curve. So he's at lowest risk for all-cause mortality based on his fasting glucose data. So from that, we can conclude that Jiraiman's glucose data was relatively youthful, and he's got healthy, as defined by the all-cause mortality data, levels of glucose. Now, next up is hemoglobin A1C. So this is a marker of what percentage of hemoglobin is glycated. So let's put his data into context. So he had values of 5, 5.3, and 5.2% for HbA1c. So blood levels of HbA1c are plotted here on the y-axis against age. And what we can see is that HbA1c significantly increases during aging. And if we take Jiraiman's average data over those three measurements, we can see that his value places him somewhere similar to a person in their 20s to 30, which is, again, 80 to 90 years younger than his chronological age. So what about all-cause mortality risk? So here we're looking at a meta-analysis of 6 studies that included about 29,000 people with HbA1c values of about 5.3 defined as the reference. And what we can see is that for values less than 5 and a little bit higher than 5.5, so somewhere around 5.8, there was no increase for all-cause mortality risk when compared with 5.3. However, people who have HbA1c values greater than 6 had a significantly increased all-cause mortality risk. So in Jiraiman's case, his average HbA1c was very close to the reference, or in other words, very close to lowest risk for all-cause mortality. So from this, we can conclude, similar to the glucose data, that Jiraiman's HbA1c is relatively youthful, and he's got healthy levels of HbA1c. All right, moving on along, white blood cells. So let's put his data into context. So here we're looking at data from the Baltimore Longitudinal Study of Aging, where about 2,800 people, were followed for more than 40 years. So starting with the baseline assessment of white blood cells, WBC, life expectancy was evaluated again up to 40 plus years after the baseline assessment. So the longest life expectancy, and note that we can look at 50% survival, so median survival. This is the time when half of the population is dead and half is alive. And because this is a longitudinal study, this is one of the rare times that I am able to say this in a video that it isn't applied to a mouse study, because we've seen this on this channel, median survival often presented. So there are very few longitudinal studies in humans, so it's nice to be able to present longitudinal data in a human study. All right, so in terms of median survival, we can see that the longest life expectancy was for people who had a white blood cell count of 3,500 to 6,000 white blood cells per microliter. So starting with that baseline assessment, they lived about 37 years starting from the baseline assessment. So what about relatively higher levels of white blood cells? In this case, towards the higher end of the range, 6,000 to 10,000 white blood cells per microliter. So we can see that their life expectancy wasn't as long as people who had 3,500 to 6,000. They lived about 30 years. And with an even shorter life expectancy were people who lived, who had white blood cells that were at the highest end of the range, so about 10,000 white blood cells per microliter. So they lived about 25 years or had a life expectancy of about 25 years, 12 years shorter than the longest life expectancy. Now, worst of them all was life expectancy for people who had white blood cells that were 3,500 or less. And as we can see, there is no median survival there because all of that population was dead 22 years later. So what about Jarahiman's data? So we can see that all of his 3 blood test measurements are within that 3,500 to 6,000 white blood cell range. So this is good. He's got the longest life expectancy or the longest life expectancy based on what his data shows. Now, there's a small downside to this, is that all white blood cells are not the same. In other words, what's the distribution for neutrophils, lymphocytes, and monocytes, which have varying changes during aging? For example, lymphocytes decline during aging, whereas neutrophils increase during aging. So that can kind of mask the overall effect if we only look at white blood cells. But that data wasn't presented in the paper, so we can't assess it. All right, next on the list, C-reactive protein, so inflammation. And what we can see from Jarahiman's three data points is that he had outstandingly low C-reactive protein at his first measurement at 115.5 years. So note that this data is in milligrams per deciliter, and if you've commonly entered your data into Levine's phenotypic age, that's in milligrams per liter. So to convert it, we multiply his data by 10. So 0.3 milligrams per liter is outstandingly low at the first measurement. But then notice that his C-reactive protein increased 6-fold at the second measurement and 10-fold when he was about 116 years old, relatively close to when he died. So let's put his data into a little bit more context than that. Here we're looking at median values for high sensitivity C-reactive protein plotted against age, with 18 to 30-year-olds, the youngest group on the left, all the way up to people older than 70 on the right. So when using Jarahiman's first data, and when considering that C-reactive protein increases during aging, as shown by the red line, so when putting Jarahiman's data into context on this picture, we can see that he would have very low levels of C-reactive protein when compared with the rest of the population. So taking that a step forward, we can assess all-cause mortality risk, and this is data for the fully adjusted model for C-reactive protein versus all-cause mortality risk. And in this study, less than 0.21 milligrams per liter was defined as a reference. And this is pretty close to as low as it can get for C-reactive protein. So Jarahiman's data, at least when he was about 112 years old, was in this range here, the 0.21 to 0.43, as he had 0.3 milligrams per liter. Now note that the confidence interval, the data in parentheses, 0.84 to 1.51, overlaps with 1. So from this we can conclude that 0.21 to 0.43 is not significantly different from the reference. In other words, he was pretty close to the lowest risk for all-cause mortality in the first measurement, 111 years old, 111 and a half years old. However, in his next 2 measurements, 1.8 and 3 milligrams per liter, that would put him here, which is pretty close to higher than everyone else in that study. And also in terms of all-cause mortality risk, it would put him in the greater than 1.02 milligrams per liter group, which had a significantly increased all-cause mortality risk. As you can see, that confidence interval is completely above 1.41 to 2.43. So note that as a potential explanation for his longevity, was Jarahiman's C-reactive protein low for most of his lifespan? So that's completely unknown. Is this 0.3 milligrams per liter at 111 and a half years old? Is this something he maintained for his whole life? Or was his data higher and then it reduced for one time point and then went back up? There's no way to know. But at the very least, that he had very low inflammation at 112 years old is very encouraging in terms of how inflammation affects us during aging and being able to potentially limit inflammation as a potential strategy to live super long, if we can keep our inflammation low. All right, moving right along, triglycerides. So let's put this data into context. Here we're looking at a meta-analysis of 61 studies, and we're looking at all-cause mortality risk on the y-axis plotted against the concentration of triglycerides on the x. And what we can see is that all-cause mortality risk significantly increases for higher levels of triglycerides. Now, at the far left side of this curve is about 90 milligrams per deciliter. So having triglycerides less than this amount is associated, or pretty close to this amount, is associated with maximally reduced all-cause mortality risk. So note that all of Jarahiman's data are less than 90 milligrams per deciliter, which would put him at lowest all-cause mortality risk based on the meta-analysis data. But we can take this a step further. Relatively low triglycerides may be a hallmark of longevity. And the reason I say that is, here's data for 11 centenarian focused studies. So you can see the average age on the right. Each of them is older than 100 years. And when we look at triglyceride levels in these centenarian studies, in these 11 studies, in 9 of the studies, triglycerides are less than 101. And in an additional study in Wilcox et al. 2008, third from the bottom, we can see that the 109-year-olds had an average triglyceride level of 93 milligrams per deciliter. So we could argue that 10 of these 11 studies had triglycerides less than 101, which is closest to lowest risk for all-cause mortality based on the meta-analysis data. So again, Jarahiman's data for triglycerides would be considered good, at least for his longevity. So moving right along in terms of what's good, and last in this group is his HDL. So let's put this data also into perspective. So HDL peaks in youth, as shown here, values of about 56 milligrams per deciliter, and then it starts to decline in the 20s, closer to 50, after which it's pretty stable over the next 50 to 60 years after that, with values in 88-year-olds in this study of about 15.9 million people, close to the low 50s. So Jarahiman's average HDL is 61.3 over those 3 measurements, which is closer to youth than the aged value of somewhere in the low 50s. Now, what about all-cause mortality risk? So this is data from that same study, and when entering Jarahiman's data of 61.3, we can see that he's pretty close to lowest all-cause mortality risk, which was defined in this, or which was identified in this study as in the 50 to 60 milligram per deciliter range. So in terms of what's good, he's got relatively youthful and healthy, based on the all-cause mortality data, levels of HDL. All right, so what about creatinine? And I didn't put this in the what's good or what's bad category, and as we'll see, it's going to get a grade of incomplete. So why is that? So superficially, creatinine levels are close to optimal based on all-cause mortality data, at least in this study of about 31,000 people. So we're looking at all-cause mortality risk plotted on the y-axis against the concentration of creatinine on the x. And when entering Jarahiman's first 2 data points for creatinine, 0.76 and 0.83, that would put him close to the lowest risk for all-cause mortality. Even in his third measurement, 0.58, risk would start to increase. As you can see, the curve starts to move upwards and to the left, but it would be far worse if his creatinine levels were less than 0.5 or higher than 1.5, which isn't the case here. Now, but note that creatinine may not be a good marker of kidney function in the age. So why is that? So here we're looking at how creatinine levels change during aging, and they're mostly stable up until the mid-60s, as shown there, but then creatinine levels start to significantly increase. And one reason for that is because kidney function declines during aging, which leads to an accumulation of creatinine in the blood as the kidneys aren't as able to filter it out so that we can pee it out. Now, adding to this story is that muscle mass is also proportional to blood levels of creatinine, as shown here. So creatinine on the y-axis plotted against muscle mass. So as muscle mass increases, because creatinine is stored within muscle, blood levels of creatinine would be higher in someone who has relatively higher levels of muscle mass. However, muscle mass declines during aging, and conversely, creatinine release from muscle declines during aging. So when considering these 2 data, that creatinine increases because of decreased kidney function, but then also decreases because of decreased muscle mass, we have to give creatinine a grade as incomplete as a marker of kidney function, because there's no way to know if his creatinine levels are good because of bad kidney function or low muscle mass. So fortunately, in this paper, they had 2 other markers of kidney function, or that we can use to assess kidney function. And the first one is Cystatin C. Now, there was only one time point that they have data for, so let's put that data into context. Now, Cystatin C is a better marker of kidney function, and I won't go into the why in this video. That's a completely separate video that I'll probably make at some point, so stay tuned for that. But Cystatin C is a better marker of kidney function in the oldest old, as it's been shown to be less sensitive to changes in muscle mass. So let's put Jarahiman's data into context in terms of aging and all-cause mortality risk. So here we're looking at Cystatin C levels on the y-axis plotted against age. And in youth, Cystatin C levels are relatively low, and that's indicative of good kidney function. However, as we can see, Cystatin C levels increase during aging, with relatively higher levels being associated with poor kidney function. And we can see by Jarahiman's data, that would put him at the far right, which means that he's got aged levels of Cystatin C, and this would be indicative of poor kidney function. So what about all-cause mortality risk? So here we're looking at all-cause mortality on the y-axis plotted against survival time. So about a 20-year follow-up starting with the initial assessment of Cystatin C. And what we can see is that people who had Cystatin C that were less than 0.7 milligrams per liter, they had the best survival. Intermediate survival for people who had up to 1.08 milligrams per liter of Cystatin C. And then the worst survival was for people who had greater than 1.08 milligrams per liter for Cystatin C. And in Jarahiman's case, he had 1.32 milligrams per liter at least when he was 115 and a half years old, which would put him for highest risk for all-cause mortality based on this one biomarker. So in terms of what's bad, Jarahiman's got aged and unhealthy levels of Cystatin C. Now, the other biomarker that I mentioned that can be used to assess kidney function is blood urea nitrogen, BUN. Now, BUN is also a marker of kidney function, assuming that there isn't a change in dietary protein intake. So assuming you have normal kidney function, if you increase your protein intake, BUN, there's data that BUN increases proportionally as urea is formed by protein deamination. So you're removing the amino group from protein and reformulating it into BUN. Now, it's unlikely that Jarahiman changed his diet over these last 4 years, dramatically increasing his protein intake. So it's more likely that this is a reflection of his kidney function. So let's see how blood urea nitrogen changes during aging, which is shown here. And if you're familiar with my channel, I've presented this data before, so this won't come as a surprise. But BUN increases during aging from values of about 13 to approaching 24 in older than 90-year-olds. Now, Jarahiman's data was even higher than the range and off the chart. At his average data over those three measurements was 27.7 milligrams per deciliter. So he's off to a bad start with blood urea nitrogen levels. What about all-cause mortality risk? So that's what's shown here, hazard ratio for all-cause mortality on the y-axis plotted against the blood urea nitrogen on the x-axis, the concentration of BUN. And what we can see from Jarahiman's 3 data is that he's on the ascending portion of this curve, which is indicative of an significantly increased all-cause mortality risk based on his blood urea nitrogen values. So when considering his Cystatin C and BUN data, we can conclude that he probably had poor kidney function over this 4-year period. All right, so what about albumin? So 3.5, 3.6, and 2.9. Let's put that data into context. So albumin levels change during aging. They decline during aging. And note that the units on this graph are different from what's in Jarahiman's data. So to keep them the same, we just divide the graph data by 10. So 4.6, values of albumin of 4.6 are found in youth, which then decline during aging, such that 100-year-olds have about 3.6 levels for albumin. And we can see that Jarahiman's data is pretty close to the age group for albumin relative to being youthful levels at about 4.6. So what about all-cause mortality risk? Well, in terms of that, relatively higher albumin is associated with a reduced all-cause mortality risk, which is shown here. So in this study, there are 3 age groups, 85 to 99, 100 to 104, and people who are older than 105 years old. And what we can see for each of these age groups was that the relatively higher levels of albumin were associated with significantly reduced all-cause mortality risk. As shown, you can see the confidence interval for albumin in each case is less than 1. Also note that other commonly measured clinical biomarkers were evaluated for their association with all-cause mortality risk. It wasn't just albumin. And we can see that the magnitude of the risk reduction for relatively higher levels of albumin was better when compared with things like HDL, LDL, HbA1c, creatinine, kidney function as measured by creatinine, and C-reactive protein. So albumin is a pretty good biomarker relative to those other biomarkers for its association with all-cause mortality risk. Now, conversely, Jarahiman didn't have relatively high levels of albumin. He's got relatively low levels, which would put him at an increased all-cause mortality risk based on his data. So from that, we can conclude that he had low and unhealthy, based on the all-cause mortality data, levels of albumin. All right, so last but not least, red blood cells. So let's put his data into context. And note that the scale on the data that I just popped up is different from his data. So to convert his data, we just divide his data by 100. So he had, when doing that, he would have values of 3.9, 4.27, and 3.89 for red blood cells. In contrast, in youth, red blood cells are about 4.8, and then they decline during aging, such that people approaching 100 years old have values less than 4.0. And along those lines, that's where Jarahiman's data was, with average values of about 4 for red blood cells. So from that, we can conclude he had aged levels of red blood cells, which is not indicative of youth, which would be about 4.8. So to summarize, Rahman had youthful and or healthy levels of glucose, HbA1c, white blood cells, C-reactive protein at least up until 112 years, triglycerides, and HDL. Data for creatinine is incomplete, whereas data for Cystatin C and blood urea nitrogen indicate that he had poor kidney function, but he also had aged and or unhealthy levels of albumin and red blood cells. So with this in mind, if we regularly monitor and optimize these and other biomarkers, can we live as long or even longer than Rahman? All right, that's all for now. If you're interested in more about my attempts to biohack aging, check us out on Patreon. Thanks for watching. I hope that you enjoyed the video. Have a great day.